Good evening, ladies and gentlemen, and welcome to the EICC and the latest in our Innovation Nation series, Innovation Bridges. As with previous innovation seminars, tonight's event is free to attend and an opportunity to hear from two expert speakers to discuss the theme of innovation bridges, a topic of particular significance to our region for many reasons. As well as the economic importance of the Forth bridges, they're also an integral part of Edinburgh's architectural heritage. Just ask anyone who's stood on the shoreline at North or South Queensferry, who will appreciate the true scale and grandeur of these great structures. The imminent opening of the new Queensferry crossing is much anticipated. So it's a real pleasure to welcome our two speakers tonight, to provide some interesting insights into the innovation that contributed to the 3 Forth crossings. Try saying that after a glass of wine. Firstly, I'd like to introduce Frank Hay of the Briggers, who is going to tell us about some of the Forth Bridge innovations and the men who created them. We will then hear from Alan Platt, who is the construction director for the Forth Crossing Bridge Constructors. And if you'd like to ask any questions, there will be a question and answer session once presentations have been concluded. But now, ladies and gentlemen, please welcome this evening's first guest speaker, Frank Hay.
Is the microphone on? Yes, good. Good evening, ladies and gentlemen. The Forth Bridge is a masterpiece of Victorian engineering. However, many of the innovations on the Forth Bridge we now take for granted, but they were viewed with amazement in their day. This evening, I'd like to cover some of these innovations and their innovators. To appreciate this, we need to go back in time. So I'm asking you to do some time travel, if you like Doctor Who and all that stuff. There were no computers. This is the 70s and 80s. No internet, no GPS, no computer-aided design. And also there was no Forth Bridge. It took hours to do that in Photoshop. The Forth Bridge starts with this man, Thomas Bouch, a very innovative engineer. He worked mainly on railways. He produced huge viaducts. He created the world's first roll-on, roll-off ferry at Granton. And he built and managed Portobello Pier. Wouldn't it be nice if we still had a pier at Portobello? And he was tasked with building bridges, railway bridges, over the Tay and the Forth. In 1878, his Tay Bridge was opened. Queen Victoria crossed over it, and for once she was amused. So much so that she knighted Bouch, and then he started what was going to be his greatest project, the Forth Bridge. This is what it would have looked like, a suspension bridge for heavy rail, and huge towers 550 feet high. The Forth Bridge is just 360 feet high, and even the road bridge is only 512. But on a very stormy night, as the train was crossing the Tay Bridge, it collapsed, killing 75 passengers and crew. Work was stopped, I should say, on the Forth Bridge, and an inquiry found that the Tay Bridge had been badly designed, badly constructed, and badly maintained, with Bouch mainly to blame. Bouch was absolutely devastated. He died a few months later after a short illness, and he's buried here in Edinburgh in the Dean Cemetery. Also, the reputation of British engineering was severely dented. The railway companies instructed their consulting engineers to reconsider the design. Sir John Fowler on the left and Benjamin Baker on the right were given the job to design a replacement bridge for Bouch's Forth Bridge. A primary requirement of it was that it had to regain public confidence. The bridge had to be not only the biggest and strongest in the world, but also the most rigid and free from vibration. And that all comes from the problems with the Tay Bridge. Fowler and Baker were partners. Fowler worked on many bridge and railway projects. He was best known for the Metropolitan Underground, the tube, in London. He devised a system to conserve energy on underground railways and experimented with trains that used hot bricks. Didn't really work very well. Baker was a junior partner, and he was more involved in the day-to-day work on site and the design. He also worked on the London Underground and on a project to transport Cleopatra's Needle from Egypt to the River Thames. People have asked what inspired Baker to create his novel design for the Forth Bridge. We think it might have been his cantilever moustache. You could say it was right under his nose. Sorry, no more jokes, don't worry. Our next bridge innovator is William Westhoven, German by birth, but he became a naturalised British citizen. He was one of the senior engineers working for the contractor, William Arrol, and was responsible for the Inch-Garvey cantilever, that's the one in the middle. He also set a new standard in engineering documentation when he wrote the first and most detailed description of the bridge, published initially in the Engineer magazine, and then it was combined as a book called The Forth Bridge, and it was a complete sellout. He lavishly illustrated this with diagrams, tables, drawings, and also Evelyn Carey's photographs. Carey was the official photographer on the Forth Bridge. He was also an engineer. Photography was part of an engineer's training in these days, and I'm using some of his images tonight. The Forth Bridge is usually described as a cantilever bridge. To be more precise, it's a cantilever and central girder. That, by the way, is a central girder. It's a very innovative and clever design. Fowler and Baker could vary the relative lengths of the central girder, that bit there, with the two cantilever arms to minimize the amount of steel. And if you can imagine, minimizing the steel minimizes the material costs, the handling costs, the labor costs, etc., etc., etc. That optimization like that is an ideal task for a computer, but they did it by hand. A second very clever feature is wind resistance or wind loading. The biggest load on the bridge is its own weight. The second biggest is not the trains, it's the wind loading. The Forth Bridge has maximum wind resistance where it has maximum strength, and minimum wind resistance where it has minimum strength. Quite a clever idea. Another requirement was that the temporary supports or false work must not impede shipping. Cantilevers are self-supporting, and the central girders were built out as extensions to them rather than being lifted into place. The Forth Bridge, so familiar to us today, was an incredulous design to the Victorian public. They'd never seen anything like it, and it was such a vast scale as well. Many people thought that the trains would run along the top of the cantilevers. Baker went to great lengths to explain this concept, and this is his human cantilever. And he gave many, many lectures during the construction of the bridge. Now, what on earth is all this about? Baker also wanted to get over just how long each of the two main spans are in comparison with existing bridges. And he came across this data for the average sizes of a Grenadier Guard sent to Egypt in 1882 and a newborn infant. These are exactly the same ratio as the length of each of the two major spans of the Forth Bridge compared to the longest span then in Britain. Now, the two arrows I've got are actually to scale, so you can see what an incredible increase in size the Forth Bridge was. Now, this photo, looking along the internal viaduct, demonstrates the sheer complexity of the design. Imagine designing, manufacturing, and assembling all these parts, all at different angles without computer-aided design. I think even IKEA would struggle to explain the assembly. The Forth Bridge is the world's first major steel bridge. Siemens Martin steel had been developed commercially in the 1860s and approved by the Board of Trade and the Royal Navy in the 1870s. This is HMS Edinburgh, seen here moored beside the Forth Bridge, was the first steel battleship of the Royal Navy, if steel was good enough for battleships, etc. Here we see William Westhoven and other engineers with their precision surveying equipment getting ready to survey the bridge site. It's very important that everything was in the right place. If we zoom in, we can see their Thomas Cook and Sons reversible levels and a Negretti and Zambra's transit theodolite. I hope you're impressed. Fowler and Baker employed the Ordnance Survey to check their engineer's survey. It reminds me of a DIY maxim, measure twice, cut once. The Ordnance Survey found a 10-inch difference. Baker wasn't impressed. He would only accept a maximum of 1/8 of an inch error on an 8,000-foot bridge. They got it right eventually, though. But what about all those funny angles of things? How on earth would you measure those? Well, Cook, the theodolite supplier, also gave them this instrument, and it has a reflector at one end so they can look up all the strange angles. Bouch set up a manufacturing plant and workshops at the top of the Hawes, Bray, at South Queensferry, and Arrol developed this further. There were large workshops, and the drill roads, we'll cover those in a minute, cement stores, timber yards, joiners, carpenters, etc., etc. There was also a small village of 16 brick houses and 40 wooden huts. At its peak, the site covered some 60 acres. The first visible sign was a 2,000-foot jetty beside the Hawes Pier. This allowed materials and equipment to be delivered by ship, and would also position the Queensferry Cantilever Foundations. Now that takes us on to the foundations. People look at these and think they're floating, but they're not really. 6 of the 12 cantilever foundations had to be built underwater to a depth of up to 90 feet. And that was a very difficult task, but a very clever device, fairly new device, was available, the Pneumatic Caisson. I believe caisson is French for big box. And a team of experienced workers had just become available. They'd finished work on the Antwerp docks. Each caisson was like an upturned cup. You can see how huge it is. It was 70 feet in diameter and had a 7-foot-high compartment at its base, which was sealed at the top but open at the foot. Compressed air was pumped into this compartment to exclude the river water. Shafts ran up to the top to airlocks to allow the men in and out and the material to be removed. And as the material was increased, the pressure had to be increased to keep the water out. And this resulted in the bends, or Caissons disease as it was called in those days. The 6 caissons were assembled on the Queensferry shore just beside the bridge. It became quite a tourist attraction. The first one was even launched by Lady Aberdeen. When completed, they were launched down the slipway and then towed into position. Enough concrete was put in them to make them sink to the riverbed. Once the caissons had reached the riverbed, compressed air was pumped into the working compartment at the foot to remove the water. The men could then start to work. A typical shift was 23 men. Shifts were initially 8 hours, but had to be reduced to 6 and 4 hours as the pressure increased to try and manage the bends. They were only beginning to understand why men were getting the bends when they worked in compression. On other bridges, previous bridges, people had actually died of this. The men could enter, at first they encountered soft mud, which could be removed by hosing it down, then opening a valve. So they opened the valve, the man at the top there, and you wouldn't be allowed to do this today, but all the muddy stuff just scooted out into the Forth. When they reached the boulder clay, which was this was the really strong stuff at the bottom, the men could hardly remove any material, even with a pickaxe. Dynamite was tried, but that was unsuccessful. But William Arrol came to the rescue. He just invented anything that needed to be done. He invented the hydraulic spade. The top of this was placed against the roof of the compartment, and the spade then sliced into the boulder clay. It took about 10 weeks on average to excavate each of the foundations. I think the new bridge maybe took a wee bit longer. But you wouldn't be allowed to do this, put men under a 500-ton weight. No, it was just floating a bit. At the desired depth, the working space and the spaces above it was filled with concrete. The temporary caisson at the top allowed the masons to make that nice granite pier, and the temporary caisson was removed. And that's how you build a Forth Bridge foundation. The caisson was a very clever device, as it not only excavated the space for the foundation, but it became the foundation. You can see on the new bridge also used caissons, but I don't think they were pneumatic. Our next Forth Bridge innovator is William Arrol, and he's a fantastic chap. William Arrol and his company played a key role in the construction of the bridge. Arrol had little education. He left school at the age of 9 to work in a cotton mill. Later he started his own engineering company, the Dalmarnock Iron Works. He was a very busy man. As well as the Forth Bridge, he was building the replacement Tay Bridge and Tower Bridge in London. Apparently he had a train that whizzed him round every week. Arrol developed so many new and novel machines to aid the construction of the Forth Bridge, it was said they did the work of 100,000 men. Which takes us on to the drill roads I mentioned earlier at South Queensferry. And here we can see one of Arrol's large multiple head drilling machines at the top in the middle, which ran on rails. Now it's estimated there were 6.5 million rivets. Some people think it was 8. But if there were 6.5 million rivets in the Forth Bridge, that means there were at least 13 million holes. Incidentally, the Siemens Martin process for the steel could use scrap steel. And 6% of the Forth Bridge steel was sent back for recycling. So there's yet another innovation. Each part of the bridge was marked off, drilled, and bolted together with the other parts, especially in the drill roads here, to check that everything fitted properly. You didn't want to find 360 feet up in the Forth that didn't quite fit. It was then dismantled and taken out to the bridge where the parts were riveted together. So the Forth Bridge was said to have been built twice. Parts were taken down an inclined plane from the workshops to the jetty to be assembled on the Queensferry cantilever, or by boat to Inchgarvie in the Fife cantilevers. Note in front of it there's a little safety boat. They had a number of these, and it's reckoned that they picked up 8,000 caps that had fallen off from the bridge during construction. The towers were built using 2 platforms. Those are right up at the top on this image. And the platforms, it was a self-generative process. They had riveting cages underneath, and then they would jack them up on hydraulic jacks. What do you do with platforms at the top when you've completed your towers? Oh, you make them into the top members. Yet another very ingenious stroke. This would be Arrol at work again. How did they rivet? Well, a number of ways. They had Arrol specialist yes, it was done by Arrol's machine, such as the hydraulic riveting cage. So this was hydraulic riveting, and this was done on the tubes, and they've got 2 of these hydraulic riveters on the cage, or by Arrol's mobile hydraulic riveter. But also there were manual teams, 4 men, well I should say 2 men and 2 boys. A rivet heater, a rivet catcher, a holder up, or a hudder up as he was called, and a riveter or hammerman. Once the towers had been built up, the cantilever arms could be built out. And this photograph must have been taken on a Sunday, the only day of rest, as there's no one working on the bridge. In 1887, Jubilee cranes, that was named after Queen Victoria's Golden Jubilee, were first used to raise the parts into place. Other bridges have copied this. The external viaducts were assembled at ground level and then raised with hydraulic jacks, while the new granite courses were inserted underneath. If we zoom in at the foot here, you can see how close some of the Briggers' accommodation was to the bridge. How old, or rather how young, were the men who built the bridge? If we zoom into this photograph, well, you can judge for yourself. The youngest death that we recorded was a 13-year-old. Children left school at 13, well, most did, and started work. However, there are reports of 10-year-olds working on the bridge, and you could leave, if you were younger than 13, school if you were a breadwinner. Good heavens. On the 4th of March 1890, on a very wet and windy day, the bridge was opened by the Prince of Wales. He got out of his train, pressed the lever to the hydraulic riveter, which closed the golden rivet, and then he jumped into the train, which took him back to the opening ceremony and a slap-up luncheon at the works. Like many great bridges we can think of, the Forth Bridge was opened later than initially scheduled. The golden rivet was actually a gilded rivet, and the rivet is still there, or at least it was when this photograph was taken. And was the reputation of British engineering and British pride restored by the building of the Forth Bridge? Well, here we have this cartoon from the magazine Punch, published 4 days after the opening of the bridge. And the caption reads, "Engineering to little Tour Fair, where are you now, my little man?" The Eiffel Tower was opened the year before. One area I think they failed to innovate on was for the safety of the workmen, or the Briggers as they were called in those days. Compare a Brigger, obviously on the right, working on the new bridge with all his safety equipment. He's on 2 wires, Every tool's on a lanyard. He's got all sorts of stuff, ear defenders, goggles, etc. The attitude to deaths and work-related accidents in Victorian times was very, very different. John Fowler stated in a presentation that a tunnel under the Hudson River had been successful as only 25 men had died. And what did the official Board of Trade say? Well, they had quarterly reports, and in their final report they stated on the Forth Bridge, 56 men had died, but in a project of that size, that was to be expected. Could you imagine that being said today? And who might this be? This man was a model for a 1950s art class in Dunfermline. The art teacher was a Mr. Hay, no relation. He was introduced as the last man still alive who had worked on the Forth Bridge. Sadly, we don't know his name. Here you can see a painter on the Forth Bridge. We don't know the date of this photo, but probably sometime in the middle of the last century. Observe the lack, again, of safety equipment. Maintaining the bridge became harder as health and safety legislation was introduced. By the start of the millennium, there was a serious concern about the state of the Forth Bridge. A restoration programme was started in 2001 by Network Rail, working with the principal contractors, Balfour Beatty, and completed in December 2011. A coating similar to that used in the North Sea oil industry was applied with an expected lifetime of 20 to 25 years. It may even last longer, we hope. The story of this restoration is available in this beautifully illustrated book. And incidentally, the bridge is now called Forth Bridge Red, but it was originally called Persian Red, a much more glamorous name, I think. And of course, the bridge has appeared in countless logos and also in very popular adverts, but surely should it not be steel blue? The Forth Bridge was inscribed as a World Heritage Site by UNESCO in July 2015. It became Scotland's 6th World Heritage Site and now enjoys the same status as the Taj Mahal and the Great Wall of China. The Forth Bridge World Heritage nomination team was led by Historic Environment Scotland, some of whom are here tonight. And this is the nomination document and represents a considerable amount of very detailed work. The team put forward 3 criteria to demonstrate the required outstanding universal value. That's OUV. That's what every World Heritage Site has to have. 2 were accepted by UNESCO, a masterpiece of Victorian engineering, and a bridge revolutionary its design, concept, materials, and enormous scale. Sorry, that's that one. Now, we've only had time to cover a few of the many innovations of the Forth Bridge, and there are many, and I've listed some here, but I think these innovations in total provide the underlying justification for its World Heritage. A World Heritage consultant, and there are such animals, pointed out that the Forth Bridge needs to be a destination. It needs a visitor centre. Network Rail announced recently that it intends to proceed with the visitor centre at South Queen's Ferry. Visitors will be able to proceed from the purpose-built centre, which has its own parking, up the Queen's Ferry Cantilever to a viewing platform, just like Sydney Harbour Bridge, maybe a wee bit smaller. Network Rail will face many hurdles and approvals, including UNESCO, who are very carefully guarding their World Heritage sites. I, for one, welcome this initiative. It will not only provide a boost for Scottish tourism, but it will also let people see at close quarters what a magnificent bridge it is. And then you've got the view from the top, which is fantastic. If you want to know more about the Forth Bridge, there's Westoven's detailed book, and that's actually free online. Or if you want the human story, a talented Edinburgh author and historian, Elspeth Wills, has written up our research. And there is, of course, the restoration book, all available online at all good bookshops. As mentioned earlier, Boucher's Tay Bridge was described as badly designed, badly constructed, and badly maintained. The Forth Bridge, I would say, is the opposite. The right people came together at the right time with the right materials and the right methods to create this wonderful bridge. And on this thought, I conclude my talk tonight.
Well, thanks very much, Frank, for a really thought-provoking talk this evening. That was really interesting. And as I said earlier on, you're going to get the chance to ask Frank some questions. Once we've heard from our next speaker, who, as I said earlier, is the construction director for the Forth Crossing Bridge Constructors. Ladies and gentlemen, please welcome our next speaker, Alan Platt.
Good evening, ladies and gentlemen. Pleased you all come along this evening. Quite a good representation this evening, really. Didn't expect anybody to come and be interested in a few bridges. But anyway, I'm Alan, the Construction Director for Fourth Crossing Bridge Constructors. My talk is largely on the back of Frank's talk to explain some of the innovations that have actually come about since 1890, is that right? 1890 through to 2017 and thereabouts. And obviously you've got a nice picture here of the bridges, which is probably my favourite, I think. So we talked very, in Frank's talk about the caissons, and the caissons were built in very small parts on the site and then floated out into position. The picture you see here is the caissons for what is now going to be called the Queen's Ferry Crossing. These were manufactured in Poland. They were manufactured in one piece and they were brought here in one piece. So the focus on this type of work is now to manufacture off-site in fixed high quality environment in order to manufacture pieces. So this caisson is approximately 45 metres high, the one in the foreground, and you probably bit of scale, this is a guy here. So these are pretty substantial pieces of kit. And again, the one in the foreground is about 3,500 tonnes. And one thing that this obviously brings in is that transportation has slightly improved since 1890. So this brings the two of them together nicely here. You have the caissons, or the remainder of, you see the caissons of the rail bridge here, and these are the caissons of the Queen's Ferry Crossing being brought in from Poland. And these are brought into position and then moved into position by cranes, which I think I've got a photo of later. Also on the transportation side, this is part of the deck sections coming from China, which no doubt I'll get some questions on why they came from China later, but all this steelwork was fabricated in China. Something in the region of 45,000 tonnes of steel was manufactured in China for the permanent and temporary works on the Queen's Ferry Crossing. So the sections you see here going across this way are actually one section of the road deck. They're also stacked up here. So this ship came from Shanghai with all the material on, and the other pieces you see, which are like the framework, they're the parts that support the deck around the tower. There's 7 of these shipments came from China to bring all the material here, and when you look at the balance of costs, irrespective of the fact that the labour rate is so much cheaper in China, the transportation cost is actually completely negligible in bringing the material from China to here relative to the cost of, or the cheapness of buying the material abroad. So going back to how new plant and equipment, Frank's rather tiny little cranes on the end of his cantilever, we now have very modern floating cranes. This is one of the caissons being lifted into position. They weren't, what was the term you used, pressurized caissons. These were just gravity caissons, so exactly the same principle, just lowered into position, and then we excavate inside, and gradually the caisson sinks down until it's on bedrock. That process did take an extraordinarily long time on the Queen's Ferry Crossing due to various difficulties. Also using the transportation and lifting theme, this is a floating shear leg crane. This came on site at some extraordinary cost, but installed about 30 or 40 pieces of major steelwork, including the frames you see on that picture that hold the deck sections. They also lifted the blue cranes up that lifted the deck sections later. And these floating cranes, there's probably in the world something about 10 or 15 of them, and they just go around the world plonking things in at very relatively cheaply, but it's obviously very quick, and they certainly had nothing like that in the 1890s. Also on the transportation theme, you can probably notice there's an extraordinary quantity of tyres here, and this is a self-propelled modular trailer, and what is on the self-propelled modular trailer is one section of the road deck. The road deck is it's 16 metres long in the road deck direction. It's 40 metres wide, which is the width of the bridge, and then it's approximately 5 metres high. That piece it's carrying is 800 tonnes, and this was assembled. The steelwork came from China, and then the concrete deck, which is across the top here, was cast on in these buildings in Rosyth Dockyard. And then basically we had a production line where 112 of these sections went into the manufacturing yard, concrete deck cast upon the top, and then brought out again and then put in the yard with these trailers. And these trailers also drove all the sections onto the barges to take them out. Again, seems extraordinarily expensive, £1.5 million to buy one of these trailers. But basically you can move huge pieces of equipment around very speedily and very conveniently. They can literally turn on their own axis round in circles. Not that we did that often, but you could do it. Here's my copied cranes from the 1890s. These blue cranes, to give you an idea of scale, you can probably just about see a guy here. So these are about 14 metres high. Each one weighs 200 tonnes, and they're about 4 metres wide. So it's a really chunky bit of kit. These again were manufactured in China. They're designed in the UK, so the engineering expertise and intelligence comes from the UK, but then cheaply manufactured in China and shipped over here. They use hydraulic strand jacks to actually lift the sections. And so this section here is actually the first section of the deck going up on the 7th of September 2015. That's the first 800-ton section going up out of the 112 that are lifted. And the last one went up in February this year, just to give you an idea of timescale. So this is the deck section lifted. You can see the lifting frame here, and this is the gap. It's brought in slightly further away from the end of the cantilever and then reversed into position. And then another innovation which we've got here, although this is not a very interesting photo, you can see these are bolted connections here, and on the table here, if anybody wants to look, there's a collection of what I think is a small bolt, but they're fairly big bolts, which are actually exactly that component which goes in these holes here. We've used in the order of about 500,000 of those bolts to join the whole of the deck section together. Another thing you can't bring along, but you can get an idea of, is that these joints here are actually welded together. So welding, again, wasn't really well known in the 1890s, but now is obviously extensively used in structural engineering. So now I get onto the cables, which is where I bring some more of my samples along. The red pipe that you can see on this here is the outer sheathing of the cables that you can see on the bridge. So when you see the bridge, if you've seen it, it has lovely white clean cables. This is a sample of the high density polyethylene pipe that goes around the cable. That certainly wasn't available in the 1890s. No plastics were. And then inside it goes the strand. So this is a small length of strand where you can see the bunch of them here. And the largest cable on the bridge has 109 of these strands inside this pipe. And each one of these is good for approximately 10 tons. So it's quite significantly strong material. Again, using winching and such like, you can see the white pipe. This is a white pipe. It's actually welded on the deck. It comes in 12-meter sections, welded together, lifted into position. And then this is one of the strands you can just see here coming out of that guy's head, going up the pipe, and that goes up to the tower top. What you'll probably be more worried about when you see it, this is the bundle of strands coming up into the tower where they're connected into this anchorage. And actually what holds that strand into position is actually these tiny little wedges, which you can have a look at later. That's actually what's holding the bridge up, just for clarity. Be very afraid. I had to bring some engineering in, partly because they didn't have computers in 1890, and I think actually they were probably better off for it, because sometimes when you look at something like this you think, maybe we've got it wrong. But there's a three-towered cable-stayed bridge is relatively unusual. There's a few in the world. This is by far the largest in the world. And one of the problems with a three-towered cable-stayed bridge is to stabilize the verticality of the central tower. As you can demonstrate by this, if the blue is loading on the bridge, so it's like a load of cars or whatever you want to say, if all the cars collected together in this location here and there was nothing on this side here, it would tend to pull the central tower over. This is obviously mildly exaggerated, just for clarity. This is a well-known phenomena in three-towered cable-stayed bridges, because in a two-towered cable-stayed bridge, you normally have a pier here, which basically anchors down the deck. So when the load comes on here, it just pulls across there and everything's fine. In this case, everything wouldn't be fine. So you have to find some mechanism of holding the tower in position, and the conventional way that's been used before is you put a guy, literally a guy like a tent guy from a tent pole, from here to this tower and another one to there, and it's just held in position. But it does look pretty hideous. So this is now the first bridge that has something called crossing stays, which is this arrangement here. So normally the cable stays would finish like that together next to each other, but in our case we've got this lattice arrangement here with the cables, and what this does is it effectively increases the structural depth of the girder, but the long and short of it, through that mechanism of that interlocked cables, it directly anchors the top of the central tower. And this is a really live innovation, because this is the first bridge that has this detail, and again developed in the UK by the team of designers here. Similar to some of the work when you were showing the arrangement of doing the riveting in a line. What's heavily used now in bridge engineering, and this is nothing new to this project, but is used quite extensively, is you launch these girders. So the principle of this is that in this area here, there's a manufacturing facility with an overhead crane, and you put a 20-meter length of the girder in position, you weld it all together, paint it, it's all perfect, and then you just push it out into the open space, and then you put another 20-meter section behind it, and you continue that process. This is the South Approach Viaduct. This is Port Edgar facility here near South Queen's Ferry, and this is a launch of 540-meter launch, taking approximately 2 years, but launching in approximately 5,000 tons of steel just out in a linear fashion in a dead straight line. So this again is the launching of the girder. You can see the two separate girders side by side, and this is just basically a guy which holds the end of the cantilever up from dipping too far down, because obviously it needs to be able to go over these piers in the process. This is a very speedy way of construction, and obviously it's entirely welded, and by the time it gets into position, it's in perfect condition. That's the whole launch there, and then later on then there's a travelling formwork that just allows the concrete to be put across the deck. And again, a very simple process, but obviously using big equipment and technology that we have today. So this is my last innovation, which also Frank talked about. We have the wind barrier, and this is the wind barrier here, which has been widely talked about. That when you drive across the Queen's Ferry crossing, when there's a high wind, no trucks will blow over. I don't know, I'd be so bold to make that statement, but the principle of it is, this is a 4 metre higher wind barrier with posts and louvers, and the louvers are made of acrylic, which is, this is actually a section cut out of the wind barrier. And the principle of it is that it diffuses the speed of the wind as it approaches the bridge, and that prevents any vehicles being blown over. Also around the tower, you can't see it on this picture, but here there'll be another large wind barrier to prevent trucks being blown over, because as anybody who travels regularly, the trucks normally get blown over at the tower because the wind accelerates around the tower and then blows the truck over immediately after. So this is a tried and tested facility. The first time this type of wind barrier was used on the Viaduct, which is a very famous high viaduct in France. And it definitely works, because I don't think they've had any trucks blow over at all on it. So that's the last of my innovations, and my talk is done.
Well, thank you very much to both Frank and Alan. We can now take some questions from the audience, and we've got 2 roving mics. So if anybody would like to raise a question, please wait until the microphone gets to you. So, over to you, the gentleman there.
Thank you very much, gentlemen, for some entertaining and really quite illuminating stuff too. I've got a question for Alan. You mentioned the difficulty in securing the caissons. What other problems are unique to this structure? In other words, unique to building this type of project in this type of location?
Certainly, my experience of building bridges is that the very fact that you need a bridge there means it's in a distinctly inhospitable location, and the weather's normally bad. And so our worst enemy on the whole project and biggest difficulty is definitely weather. And the way we design everything is based around temporary works, making sure that the access is available and we can beat the weather. Frankly, we haven't been 100% successful on that, but we're trying. General challenges, there's been the caissons and settling those down. There's the temporary supports that supported the deck in the middle at the piers. We also had problems with those, and actually the photo that Frank had of the guy sitting on the steelwork there was actually...
It's actually my son-in-law.
Is it? He was actually doing part of the repair work.
He's an Alpine class climber.
Yeah. I mean, currently we have, I can't remember, something in the order of 50 abseilers on site doing various work where, frankly, it's just implausible to get access to. It will have future access and things, but it doesn't have it at the moment. Bridges are a challenge. That's probably why I like them. I mean, virtually everything is some type of challenge, but generally weather, lifting, tides, wave height, everything. You have to fight everything every day.
Okay, thank you. Who else would like to ask a question? The gentleman there.
Yeah, I've been driving across the other bridge quite often, and one of the fascinating things is that the road deck at various times, as you're putting sections in, particularly as it began to reach the opposite deck, varied enormously, in terms of whether they were going to meet up. And I wondered how presumably that was with the tensioning of the cables. Is that what brought them finally into line? And how on earth do you tension cables of that sort?
Okay, I'll do the first question. I never worried about them joining up. I don't think anybody did, actually. To give you an idea of how flexible the bridge is, when on the centre tower you had the massive balanced cantilever, when you lifted a deck section up on the last one, the deck lowered 4.5 metres, and the tower moved 1 metre. So that just gives you an idea of the flexibility of the structure. So that's what you would have seen. We would have been out of balance by one section extra would be on this one, which is 800 tonnes at 300 metre extension, and there'd be one missing off the other side. And then when the one came back, it just seesaws back and forward. When you actually get to the joint position, we were probably about 200 millimetres, so 8 inches away from level. And all you do is just drive some trucks up the high side, and it comes down, and then you bolt it up.
Wow.
Sorry?
The cables.
Ah, right. Okay. It'd be handy going back. Can I go back on the presentation? Because go on, carry on. Back a few. Back. Okay, you're getting there. Nearly. Back of one. Right. Okay. See that there's a hydraulic cylinder there. Each of the strands is individually adjusted, so you know exactly what length the cable has to be. So you just keep on pulling it until it's the right length, and then you just keep on doing that. You do that with the first one, and then you do it for the second. You just keep on going, and then you just do a check at the end. But we did have a seriously big jack that could actually adjust the whole strand, which would lift basically 1,500 tonnes at a time. And we did have to do some adjustments with that type of gear as well. So it's relatively easy.
Has been also watching it, but she had a question too.
What I wondered was the cranes that were manufactured in China, who supervised the quality control to make sure that they were satisfactory for the work?
Okay, if you decide to buy your steel in China, you have to adequately supervise to keep them honest, to put it that way. So in the manufacture of the steel deck, there was about 40 expatriates, generally from the UK, actually looking after that manufacturing. They were based in China in the factory, and they're looking at it every day. Some of the steel deck here is some of the best quality steel I've seen from General Quality. You wouldn't get it better anywhere else. And similarly, the cranes and all the support steel work, all of it, well, a lot of it was manufactured in China. It is pretty good quality. But you have to put people in to look after it.
Okay, thank you. Question here?
You've got to get a question eventually.
No, I'm quite happy. Ask Alan all the questions.
This again is for Alan because, as you know, when you cross the current bridge, it's thud, thud, thud,
Yep.
all the way across. Are you going to get the same in the new bridge?
No.
Good.
That's a quick answer.
And when does the new one open?
Okay, I'll answer the first one in more detail. It's a massive innovation since even since 1964, I think, when the road bridge opened. The expansion joint technology is such that there's only 2 expansion joints on the new bridge. One is where it meets the land on the south. The other is it meets the land on the north. The one on the south is the biggest expansion joint ever made, which accommodates 2.3 metres of movement. And the one on the other end is 1.7 metres. and then it's a continuous asphalt deck for the whole length. The other question is, I do know the answer, but I'm not going to tell you. Well, as you know, this was meant to be timed exactly for the opening of the bridge, but it just came too early, this presentation. So we've got a window now that's agreed with the government between the 21st of July and the 31st of August. And the simple answer is we're within that window.
Okay, thank you. Got a question at the back there. So that's July and August this year. No, that's fine. That's fine. That's fine. Yeah.
Whose side's there?
I have a question for Frank, which is a simple one. Is the Forth Bridge still the largest cantilever span in the world?
Miles, you might actually know that. I'm afraid I don't.
It is. I can tell you that. It is.
Yeah, it is, yeah.
Okay, it's not. It's the Quebec Bridge.
Yeah, but it only has two.
It has two, and it's cheating.
Yes.
And the reason it's interesting is because it was constructed in a different way to the innovative way you described, with the suspended span in the middle being actually lifted
Yes.
in a complete form from the river beneath. And it was proved to be a catastrophic choice, and it collapsed, in fact, twice.
Yep.
Killing far more people than wherever. And this was 1917 when it was finally completed. Again, the Forth Bridge was hugely superior, even in terms of a bridge that was built, completed in 1917.
The consultant for the Quebec Bridge came over and made very derogatory remarks about our lovely bridge. He said he could have built it for half the cost, used half the steel. He went back to Canada, and as you say, the bridge fell down, killing more people in 7 minutes than the Forth Bridge did in 7 years.
It's incredible. Okay, next question. This gentleman here. John?
Hi, I'm interested in the total project costs if you adjust, the old bridge for inflation, etc., so bring it to today's date. Just wondering, and then also the ongoing maintenance costs point forward from here, what we're expecting relative between each of the bridges.
Well, the Forth Bridge was costed, I think, around about 2 million originally, but it came out at about 3.5 million. It was also, I think, originally about 2 years late. They hoped to finish it around about 87, 88. I don't have the figure in today's money, which would be useful, but I think it's quite a lot.
Ours is, or the contract price was 790 million. It's cost significantly more than that. And that's a subject for discussion, as they say. I don't really know what the relative cost would be. I would imagine. Yeah, we'll work that one out next time. Maintenance cost wise, the new bridge is designed for very economic maintenance. The concrete deck is virtually maintenance free. The steel. The steel work and the painting all has access provisions, which is included in the contract. There's a climbing cradle that climbs up the cables, and one that goes up the towers. There's a lift inside all the towers from the deck up to the top, and you can replace one of the cables. You can take one of the cables out completely, and the bridge is still completely sound. You can run full traffic on it. So I mean, it's a properly whole life costed project, including the maintenance, and very well specified by Transport Scotland. In fact, it was a bit tough actually, but it's there.
Okay. Sir. John, just this gentleman here. Thank you.
This is for Frank. Do we have any dates for the visitor centre that's going on to the top of the
Well,
bridge?
had we been in Queensferry, Craig Bowman, who's in charge of that, is actually giving a talk on that. I think he was talking about 2020 maybe, but it's got so many hurdles, and it's a very good point. I think we should all support Craig and Network Rail in this. He's got so many hurdles internally and externally to get approvals. Think of the local approvals. And of course they hope to build the more general one in North Queensferry, but the people in North Queensferry do not like visitors, and there's been a huge fuss there. Well, it's understandable. Getting cars in and out is really quite difficult. South Queensferry is bad enough. But yes, I mean, it's round about that date, I would say 2020.
Thank you very much.
Okay, I think we've got time for one more question. This gentleman here. John, sorry. Yes.
We'll definitely get you to ask your question.
My basic question is that the fourth bridge was paid for by the railway companies, so it was a purely commercial concern. There was no public money involved. Do you think that helped drive the innovation for the bridge?
That's an interesting point. There was railway mania, wasn't there? I mean, if you look at the railway network in Scotland, it was quite well advanced by Scottish standards, but nothing like what it was, the density in England. I think that what with innovations is driven by, if you look at engineering really over that century, over the 19th century, it was moving from craft to science. And there's so much science coming in on metallurgy, even on medicine. We haven't touched that, but the local doctor was writing a thesis on the effect of compressed air in the body. And I think you had, to me, innovation tends to be, we think about mobile phones and computers and so on. It's really about people. And as I said, the right people came together. And Arrol would just brilliantly think up a machine when anything that was needed. He had machines all over the place. And I think that spread. He was very highly respected by his staff as well. And I think Fowler, Baker and Arrol chose the best. And that's where the innovation, and they encouraged it, came from.
Okay. I think this lady down here wanted just to ask a question. That was the last one.
Yeah, it's fairly simple. When we saw the caissons floating, were they on a pontoon?
Yes. Well, on a vessel that can submerge itself.
Right. And had they come from Poland on that?
Yeah.
Good heavens.
The obvious thing, it looks unstable. I think that's what you're saying. It looks like it's unstable. I look at things like the new Queen Mary and think that it's got 11 metres under the water and it's got like 40 or 50 metres above, and it's largely the same as that. But the actual centre of gravity of the vessel is virtually at water level. Yeah, it looks scary.
On that happy note,
Could I just mention one thing?
Sure.
I was talking a lot about about cantilevers and how many people know what a cantilever is. Alan's brought these lovely nuts and bolts along, so I thought I would bring along a cantilever. And a cantilever is a beam supported at one end, and we've all got them in our house. It's a shelf bracket.
Very good. So, thank you very much. So that brings our session to a close, and I'd like to thank you all for coming tonight. Thank you. And also, and of course, to Frank and Alan for giving up their spare time to speak to us this evening. So, thank you very much. And I hope that you've all enjoyed Innovation Nation, and please do spread the word to your family, friends and colleagues. Our next Innovation Nation evening is on Thursday the 15th of June under the theme of Innovation Robotics. So we hope to see you there. And in the meantime, feel free to enjoy a glass of wine or soft drink outside. And I think both Frank and Alan are going to hang around if you want to have a chat. So thank you very much.